Okay, let's see if this is coming through now. Okay, looks like we got audio. I guess that's fine. Okay. All right, so welcome back to class for Monday. Hopefully everybody had a good weekend. I thought I would talk about the homeworks and stuff. We'll do just a little quick review. So let's see here. All right, so the I got to find the right window. We're going to talk about the next homework assignment, but let me open up the previous one. So homework 1, so these are, I did make a couple of changes to the syllabus, but they're mostly just to change things that we're not really utilizing. For example, we don't have a makefile or a Visual Studio solution. That's just kind of a generic thing I had in my syllabus template. So the new versions going forth will be making sure that your source code on GitHub clearly demonstrates the main requirement and that your source code on GitHub is neat and documented. So I just wanted to make sure that that was clarified, and then I went ahead and adjusted the rubric on Blackboard. So I use this rubric just basically so I can kind of mark where I think that you are. So hopefully, if you cannot see it, then please let me know. Just say it's not turned on. So I have to remember to set the switch that says show the rubric to the student when I grade. So hopefully that's visible going forward. Anyways, that's what I changed. So I updated that on the syllabus. So the syllabus on Blackboard has been updated to reflect that. Don't think it really changes anything aside from just making those more clear. Okay. Let's see here. I noticed on 1 or 2 of the turn-in homeworks that the matrices weren't formatting correctly, and that's because I forgot to include a package inside the LaTeX template. So you might want to go over to the LaTeX template and update it slightly. So move this out of the way.
The other thing on that, the example code that you gave, as it was exported as a PDF, it got included as an image, and so we couldn't copy and paste any of it.
Oh, gotcha.
If you don't want us to copy and paste it, that's fine, but it was a little bit of annoying to reverse engineer it.
Sorry. So actually, to help you out with that, so in the preamble, I forgot to include the AMS math package, which basically lets you do math. Not sure how I forgot that, but I did. But inside the main, I just kind of clarified, 4 to 5 sentences for paragraphs here. And inside the answer section, let me move this out of the way, I can't see myself. Inside let me hit recompile. For some reason on my computer, it's been like flipping everything backwards. If I switch windows, it's kind of annoying. Okay, so you'll see over here on that the math equations that I put in the template are right here. So this should make the matrix stuff go a little smoother. And you'll see right here that I just put the code in here. So that hopefully should fix the issue that you just brought up. So apologize if that added a little extra time to your do a weekend. And then I went ahead and, so the sections, unless I don't ask for it, there's like some additional sections for the additional requirements. This is just so I can see what you did. So you can highlight the source code that kind of says, here's this particular element. Because if I ask you to do like a test, like, show how you would do a matrix operation or something, I don't necessarily mean for you to write a completely separate program just to do that. I just want to see what you would do inside that, if it's Unreal or Unity or whatever the case. So, so there are those changes. So go ahead and it's the same link as before. So just go ahead and you just copy and paste those elements out of it. So hopefully that should help.
So wants to resubmit one the new section?
No, you don't need to do that. If you're doing the math, you can copy the preamble, no problem. It'll fix the math issue if you're having it. And then this will just be going for the homeworks going forward. I don't want you to go back and redo a bunch of stuff. Okay, so there's that. Let's take a look at homework number 2. So I know that everybody's still working a little bit on homework 1. I know one of the issues is that, and this pretty much happened across the board, is every GitHub repository, except maybe one, didn't have source code or anything. It's like they're all blank. And so either it was a case of you forgot to push back up into GitHub, or some people had difficulty because they had large files that wouldn't go back up unless you had the right git ignore settings in there. So if you run into those issues, I would encourage you talking to the chat room so you can help each other out in terms of, these are issues that don't necessarily come up in like a CS201 class because your files just aren't that big. But then when you start working on like projects you might be expected to work on nowadays, then you might be talking large file sizes for absolutely no reason at all than just to have large files. I kind of grew up with floppy disks, so to me, like, some of these programs shouldn't be more than a megabyte, but instantly when you start a Unity project, it's 27 megabytes just with nothing ready because of all the DLLs that are going in there. So, and then you want to make sure that you package up your program so that I can run it. So, one option is just so make it easy to find your build. And then if you need to, like there was one project's using Panda 3D, so I'm going to try installing Panda 3D on my system because that one has like a gazillion DLL files that all need to be like configured just the right way. So if you need me to have some kind of development environment that will run your program out of the box, then just arrange that with me beforehand so we can kind of get that squared away. How many people I guess are getting a feeling for how hard graphics is? Yeah, I think most people. There's this
thing that I ran into with when I was building with the Unity engine. So much of the generic matrix and vector math has built-in functions that hide all the hidden stuff, and so it took me quite a while to get to a point where I could find something that I could do with the actual matrix raw math.
I'm going to find this one video. That I think I think it was this video. It might not be this video, but let me just see.
CPU, which is the same thing that powers Apple II. All right.
Okay, so I don't know if the audio. Oh, I know why the audio is going through. Okay, so I have to do that. Let's watch this video. We're just going to watch half the video, but I thought he did a very good job talking about what graphics is like.
Isn't that a cool slide?
Okay, so I gotta mute the computer and unmute the microphone. Yeah, so what I liked about that video is that I feel like it echoes every single attempt that you decide to do graphics. As soon as you don't touch it for a couple of months, that's what happens. It takes a lot of effort just to get a black screen ready to go. And I'm sure that, you know, I asked a lot from you the first couple of homeworks, like, hey, just go make a game, you know, just I'd like to see a game over the weekend, you know, something you can start, stop, play, has rules, all that kind of stuff. And probably what most of you found out is that you picked an API and it took a while to kind of get it started. You know, you might be able to get something simple spinning on the screen, but it does take a little bit of startup time. So what I would encourage you to do is, you know, take your, so I'm not going to have like late homework for homework 1, but I'd like you to finish it. That way, when you do homework 2, you're building off of what you just did for homework 1, okay? So in the same way that, you know, I showed you the code that I did for 1 hour game jam. The first one wasn't exactly exciting. I just clicked the button to have a game go. And then I just built on top of that over the next few weeks. And so that's what we want to do, especially considering that homework 4 or 5 is the Ludum Dare challenge, which is October 6th when it starts. So you at least want to get to the point where you can make a game that works. And I have some helpful stuff to show you today. Okay, so let's take a look at homework 2. This is still a draft form. It's almost done. So the idea here is we're going to have some questions, kind of talk about the mathematics side. So I'd like you to, you know, multiply these matrices out, a rotation matrix and a translation matrix, and find out what happens when you do it backwards. Okay, and just I want you to think about this kind of stuff, because when you're debugging how something's moving on a screen and you're using these matrices, you need to be able to understand what's happening and why it's happening. So that, and then the second half is kind of trying to understand the vector cross product. Last time we were talking about the dot product, and the most important information on that is the cosine of 2 vectors. We're trying to find out what is the angle between 2 vectors, and the cosine is normally what we want. Sometimes we don't even need to know the angle, but the cosine allows us to get the angle, or in and of itself is extremely useful. Okay, so that most likely would be a test question, knowing the cosine. Okay. Okay, so the main requirement is to do the 1 hour game jam. So this week's jam was virtual pet, and I don't know what this Saturday's, that's always up in the air. Okay, so this time we'd like to work on getting a playable video game. Okay, so for homework 1, I think it's just enough that you got something going, that, you know, you can move something around on the screen. But then I think by the time we get to homework 2, we should be able to have a game, even if it's just something simple, right? And we can talk a little bit about the Atari 2600. Everybody heard of the Atari 2600? This is so old, it's like, what are you talking about? I'll talk about the Atari 2600 a little bit today before we get into the math. Okay, but these are the kind of things I want you to think about in your design paragraph. So, you know, what are the rules for your video game? I want you to kind of think of a concept of, you know, what I want to make this game about. How does a player win or lose? How is the game started by the player? And can the player pause the action? So these are some of the mechanical things that just kind of need to be in there. And having these, a few of these implemented already makes your game like feel like a game, you know. Most people would think it's weird if you were to download like the latest version of, I don't know, Final Fantasy or something, and then it just pops in the middle of an action sequence, and you're like, whoa, what's happening? You know, you would expect the title screen and being able to start and change your options and all. Some of those things, it just feels like that they belong to a game, right? Okay, and then the additional requirements. So you'll pick 2, unless you're a grad student, you'll pick 3. And you can pick any one of these. It doesn't have to be like you have to do 1 and 2. So if you want to do 1 and 3, or 2 and 3, or 1 and 2. So one of them, I think I'm still working on number one. I haven't decided what to do yet on that one, but the one is do a quick section on how do you do transformations with your 3D engine. Okay, so we're thinking about matrices like scaling, translation, rotation, and look at. Okay, so write 2 paragraphs to kind of show how you would do that. And then another one is create a diagram showing the state logic of your video game. So I found this really great website called draw.io. And this website, I don't know if I may have closed it. Let's see here. Go to draw.io. I think I was working on this other. Create new diagram. Sure. Just create a blank one. So this software online allows you to just kind of grab objects, and we could say that's like game start or something like that. And then you can just quickly build diagrams very easily with this piece of software. So you know, normally in the past you'd have to like get something like Visio or some other kind of fancy drawing package, and this one's really nice. You can get started really quickly, and you can do it online and just save you work locally. All right, so this is something I would recommend. Let's go over here. Okay, so as a helpful thing, I thought I'll include this. I call it helpful diagram, but here are a lot of things that might go into like a basic game. So sometimes it takes a little bit of thinking to kind of come up with a structure like this, but it does kind of provide the framework. So you can kind of tell exactly how you would need to implement this inside your engine. So for instance, when the program starts, you'd have to initialize everything, right? That includes loading graphics. If it's like Unity or something, that's already done for you automatically. It's already kind of built in. But it might be, hey, load level 0 or the main menu. You know, maybe there's a scene-based organization there. And the first thing, you know, show the main screen, and then from there you can either quit the game or start the game, and then you would initialize the level, and then you kind of go into a loop here. So checking player input, doing any game logic, checking if the game's been won or lost. You know, if not, you just kind of keep looping there. If you need to pause the game, if I have some way of moving the game into this pause state and until they unpause it, and then, you know, if the game was won or lost, then you can say, okay, go to the won screen, and then you might want to wait for input so it doesn't just flash by in a second and then you're back in the main menu. Okay, and then maybe you have multiple levels, so you could do level finished and decide what you should do for the next one. So I think this has like a lot of the basic parts to just a straight up classic arcade game, you know, that you might see. All the bare basics that you would need to kind of organize how you approach a project like this. So hopefully that is of some help. Okay, so that's going to be homework number 2, and I would encourage you that if you really liked the last 1 hour game jam theme, to kind of go along with it. And a lot of times with game jam themes, you can make them anything you want to be. So it might say virtual pet, but that doesn't mean like it has to be a Tamagotchi. It could be, you know, Super Mario, but he's got a pet walking behind him or something. You can, if you want to do a platformer, or you want to do a strategy game or whatever, you know, you can make the theme fit that your project. So now is a good time to kind of think about which kind of a game project you'd like to work on. And maybe it's connected to the journey project that you're working on as well. So if you're trying to think, you know, how best you'd like to do that, then it's a good way to get practice there. Okay. Any questions on homework 2? All right. All right. And then as always, you know, my comments typically on homework I try to make them short. So that means they're not personal. They're just like, you know, you might want to change this in the future or something like that. So don't read a mean tone into it, in case I am kind of a red pen person. Just like, no, wrong. But, you know, come see me if you have questions about, and I can help you get, you know, show you where we're trying to get to. So, and I do understand that, like with graphics, I used this analogy earlier today. It's kind of like nobody ever thinks that, you know, the first step into doing graphics is just hitting a wall that you have to like climb before you kind of get to the gentle slopes above, you know. So we're just trying to work through those initial problems that everybody has when they get into graphics. Okay. Okay, so we talked about homework. Talked about the project report there. All right, so let's talk about, before we get into the math today, is the Atari 2600. And the Atari 2600, I think, is, you know, it's pretty famous for being one of the first like home consoles that you could buy. And one of the things I appreciated about it is that if you look at a lot of the games for the Atari 2600, a lot of games have just copied the concepts. Like you can still go back and look at Atari 2600 games, and you're like, I see this nowadays in this game or that game. You can see there's all these patterns. One thing I liked about the architecture is that you had 128 bytes of RAM. So if you could imagine what kind of game could I write with only 128 bytes of RAM, just kind of working scratch memory. It doesn't feel like a lot, but surprisingly, you can do quite a bit. And the other thing about it is the joystick controls were very simple. So you just have to go up, down, left, right, and you have a button, and you just use that to kind of figure out your way through each game state. So that's one way of kind of help narrow down the scope of a 3D game, because nowadays, you know, there's a lot of competition. You know, a lot of time goes into developing like an easy to use user interface for a video game. However, it does take a lot of work just to implement all those controls. I mean, if you think about looking up, looking down, strafing left and right, you know, you might do rolling, mouse look. You have a lot of different ways that players like to interact with their with games nowadays. And so, yeah, professional developers spend a lot of time working on that, which in this class is fine. It would take months to work on that, though, to get it all the bugs ironed out. So it's probably a good idea to figure out how can I design the easiest control solution now. That way I don't have to worry about that. I can use that to do whatever I want. Okay. Another thing that I liked about the Atari 2600 is it had some built-in hardware for doing sprites. It had a player graphic for 2 people. It had a ball character, so that could be like a weapon that was fired, 1 each for each player, and then it had a way of drawing the background. So if you think of it that way, as you're developing your graphics for your game, kind of think about how can I make it the simplest architecture possible so that as I'm doing my game logic, I'm just updating a few different variables. And don't worry so much about adding, you know, crazy amounts of enemies, or, you know, just kind of learn how to work with just a few items, a few objects interacting with each other, rather than trying to come up with something very complicated, because those just take practice. As you get better working with like onesie twosies kind of thing, then you can expand your algorithms to work with larger amounts of enemies and so on. But it's best to have just a few that you're working with. Okay. Let me see if I can find a GIF of combat. This is like one of the first games that. Oh, there's one. Let's see here. Well, fine. We can look at this one. This is fine. Okay. So, believe it or not, to get a game of this complexity going would probably take you about 2 or 3 weeks to to kind of get up and running if you weren't working on it like every single day. And I know this because I taught a bunch of high schoolers this last summer how to make video games in Unity. And it took us about 2 weeks to get a game that was not even this capability, and that's working every day on a little bit of it. So don't be too frustrated if the progress seems to go slow, but as long as you have a plan to kind of get to a certain, a certain goal, then as long as you're making progress, that'll be, if you can break those steps up so that you can kind of get to one milestone, So milestone 1 for homework 1 might be, let's just get the player to move around. Milestone 2 might be, let's let the player interact with something else on the screen, and just kind of go from there. All right. So let's take a look at, and then of course there's additional things that you have to consider that are, I'll call them optional at this point, but they're things that would definitely help improve the quality. Things like sound effects or graphics. Adding those kinds of things. So hopefully those are easier to add than maybe some of the techniques that you have to worry about. But those are additional things you have to think about as well to polish up the game. So let me find console here. Yeah, the original combat game was only 2 kilobytes. So the actual program itself was 2,000 bytes long. It wasn't very, it's pretty simple. But if you could imagine writing 2,000 lines of code and debugging it, that does take a little bit of a time. So there you go, it's 120 bytes of RAM, and that's for your stack. And then the graphics basically, they didn't have a frame buffer, but in our case, think of these they had these 8-pixel bitmap sprites, missile sprites, a 1-pixel ball, and a 40-pixel playfield. So if you can just kind of narrow down what you're trying to do to just like I said, just make those a checklist. Can I do this? Can I do that? And then that way you have, as you're working on each part, you're able to kind of get those working. And then I would encourage you, just go on YouTube and watch videos of Atari 2600 games and kind of get it, or download a emulator that you can kind of try them out and just kind of see how simple some of the stuff is, and you might find something that you enjoy playing. But you'd be surprised how many of these concepts have just kind of carried through modern games. All right, any questions? Okay, so there's some homework. Go nerd out on the Atari 2600, look at the games and get an idea of what you could do with the, what would you do if that's all you had to work with? And I bet you come up with a lot of different ideas. And it's something you can apply to your graphics engine that you're using now. Okay, so last time we were talking about, we were finishing up by talking about matrices. Okay, so we covered a little bit about, we just go back to the beginning. So we had the quick intro. So we were talking about two-dimensional math and basic skills that you just need to know. So adding and subtracting vectors together or points. How do you multiply vectors together? And we saw the two main products there were the dot product and the cross product. Dot product gives you the cosine between the two angles, and especially if they're unit length. In other words, they have a length of 1. And we said that the length of a vector is, you just take each component, square it, add them, take the square root, okay? And so you can get the cosine by taking the dot product, and then the cross product is related to the sine, but more importantly, it gives you the vector that's perpendicular or orthogonal to the two original vectors. So if you're trying to find out what direction a polygon was pointing, you can construct two edges out of, the triangle has 3 vertices, so you construct 2 edges out of it, and then you can take the cross product of those 2 edges, and that'll give you the face normal for the polygon. So cross product's very important, and dot product is very important as well. And length is what more or less you use the length for 2 purposes. One, you could use the length of, you just take the difference between 2 points, And then you can find out how far are 2 points from each other, and that's where you would take the length. So take the length of the difference of 2 points. Or to normalize a vector. So you have a vector, it could be 5 units long, but you want it to be unit length. You just divide by the magnitude. So every component just gets the magnitude divided, and then you get a length of 1. Okay, then you have, we talked about geometric algebra. So we kind of talked about how do matrices form a vector space, and we were taking a look at how when you do certain rules in mathematics that we get this idea, we can derive the dot product, we can derive the cross product, and we see that we can use some higher order math to allow us to understand these concepts better, and how they actually are not as complicated as we might think they are, although they do take some practice to get used to. We talked about 3 kinds of transforms. There's the linear transform that preserves vector addition and scalar multiplication. That's more like the underlying theory. So I would expect if you're taking linear algebra that you'd have to prove some cases of why, show in this system that this is true, for instance. Okay, but this is more underlying theory, so we're not going to do that. But it is helpful to know that like a rotation is a linear transform. So you could take the rotation matrix and show that this is true. Then you have a affine transformation, and so that one is a linear transform and then a translation. And that one preserves parallelism of lines, but not necessarily lengths or angles. Okay, so this is most of our like rotation, scaling, steering matrices, and so on. And then you have an orthogonal matrix, which means that its inverse is the transpose. So one way of proving that would be to take like a rotation matrix, take the transpose, and if you multiply them, you should get the identity matrix out, because by definition, a matrix times the inverse is the identity matrix. So if you wanted to quickly check to see if a matrix is orthogonal, just take the transpose and multiply it and see what happens. Okay. All right, so there's geometric algebra. This is going to come into play when we're going to talk about quaternions a little bit today. So, and get a feel for that. And then we're going to take a look at if you were going to do graphics from scratch, how might you do that? And I'm going to show you how you might get a basic graphics screen working with GLFW. I used to like to use GLUT, which is the GL utility toolkit, but it hasn't been very well maintained over the years, and GLFW does basically the same thing, but I think it's more streamlined. So I'll show you how you would do graphics with GLUT, although there are other libraries you could equally use, like libsdl2. That's also very popular if you're building graphics from scratch. And as we go through the next couple of weeks, we'll kind of explore how do you do some low-level graphics, all right? Sometimes when you're using Unity or Unreal, all the bare basic stuff is like hidden from you. Okay, so yeah, matrices. In this class, we mostly care about 3x3 and 4x4 matrices. We care about 3x3 matrices because they're good for transforming vectors. We care about 4x4 vectors because they allow us to transform homogeneous coordinates, and that's the one where we add W. And if W is 0, it acts just like a vector. If W is 1, then it acts like a point in space. Okay, so we talked about the transpose and the determinant. The determinant's handy because if the determinant is not 0, then it has an inverse. Okay, so if it is 0, then you're not going to find an inverse in that. That matrix is all sorts of messed up, probably, for 3D graphics. Okay, so we talked about how to multiply them together and how to transform a vector. So this is important to know how to do because we want to see how, say how a vector, how your points in your model end up going to be something you can do on the screen. All right, I know that's we need to be able to understand that. We're going to talk a little bit about that today. Okay, all right, so we have a few different kinds of matrices that are very useful. The first one is the translation matrix. And in this matrix, we just, we want to offset a point by a certain number of, units in the X, Y, or Z direction. And one of the things you might be considering is like, well, why don't we just add this directly to the point? I mean, it seems kind of, if you just look, if we look back here, we have 16 multiplies and 12 adds. So why are we doing all this work for just like moving a point around? Well, the short answer to that is that you can concatenate your matrices together and then do everything in one step. So that's going to be one of the homework questions. So if you wanted to, you could just calculate your projection matrix, your view matrix, your world matrix, and stick them all together in one matrix. And then in one step, then you can transform your point. And that's actually very useful because now where you would have had to do a whole bunch of intermediate steps to get where you want to, you can just do everything with one mathematical tool. So this matrix is very useful for 3D graphics. And so what we do is we just put it in the fourth column, and this is why we need homogeneous coordinates. And what this will do is just cause the, if you notice from the homework problem, we just end up adding that translation component to the very end. So you can see that it's built in. Scaling matrices are useful when you want to make an object larger or smaller. Although they do have a downside. Well, it's not 100% a downside, but if you're, normally what happens when you're going to transform your 3D model, you're not just transforming the geometric points in the model, you're also transforming the normals, so what direction the vertices are facing, and what the scaling matrix will do is it'll take normals, which are typically unit length, because we want them to be unit length, and then make them not unit length anymore. So that means that you're going to have to renormalize the normal for your geometry. Now, approximately how many pixels is in a HD monitor, 1920 by 1080? How many pixels is that approximately? What's that? Millions, yeah, you got millions. So how does everybody feel about doing a square root for every pixel? Does that sound okay? It doesn't sound good at all, right? But surprise, 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 we do it all the time in 3D graphics. We live in a day where you can just like take square roots and throw sines and cosines around and do all sorts of crazy mathematics for every single pixel, okay? So ironically nowadays, because if you think about it, if your nice graphics card can do like 1 trillion operations per second, and you're talking millions of pixels, then you can, no joke, you can do like 1 million operations or so on all those pixels. You got to divide by frame rate though. So now you're down to about 10,000. So if you really wanted to, you could do like thousands of operations on every pixel nowadays in computer graphics. It's actually kind of mind-blowing when you think how much computation you can do per pixel nowadays. Okay, and that's why graphics are starting to look so good, is because we can just throw compute power like it's nobody's business at these graphics problems. Okay, so yeah, scaling matrices, in the 90s, you kind of cringed like, oh, I got to normalize these vectors after I'm done. But nowadays, it's like, okay, just do it. And that's one of the things that's important to understand is sometimes you have the option of computing something, and sometimes you have the option of storing something. Okay, and this is a reality when you think about. You might be tempted to pre-calculate something because you're worried about how fast or how long it's going to take to calculate it out. And in some cases, if you look at how long it actually takes to get a piece of memory across the bus to the CPU, you may have been able to do that operation 10 times over before you even get it out of memory. So we're moving to a time where in a lot of cases, it's just faster to recompute than it is to store. And so this is something that, so I would encourage you that you don't really need to care about it. Just compute until you need to store, all right? Okay, rotation matrix. So this is probably the easiest one to remember. This is one you absolutely should remember. And this is just, it rotates around the z-axis. And if you were to, if you wanted to rotate a point, well, I guess if you recall from trigonometry, if you were to calculate the parametric, equation for a circle, your x coordinate would equal cosine theta, your y coordinate would equal sine theta. So if we look in our first column here, for what would represent the x-axis, you'll see that cosine theta and sine theta, that basically represents that equation. Okay, but we're not just rotating coordinates in the x, we're also rotating coordinates on the y-axis as well. So this is why we have the second set of sine and cosine on the other side. So you should remember how to do this. And the y and x ones they coincide. And this is the equations you would use if you're going to represent a rotation as a set of Euler yaw, pitch, and roll. So you would just say, okay, how much do I rotate on the x? How much do I rotate on the y? And how much do I rotate on the z? The only issue with that, has anybody ever heard of gimbal lock? Yeah? So what's gimbal lock?
Where basically you rotated your around one axis, and then you rotate around your next axis, and you rotate around your third axis, but now, you're looking horizontally at the thing that you're trying to do, and you're trying to get over to where you actually want to look.
Right. It messes with you. So like if you were to use the Euler angles for representing a 3D rotation, like let's just say you're going to represent a plane, and you have theta x, theta y, theta z, and you say, okay, I'm going to turn a little bit this way, and then I'm going to turn a little bit this way, and turn a little bit this way. Well, as you accumulate those rotations on the x, y, and z, all of a sudden, it won't be long until your plane just feels like it's all sorts of messed up. And so they don't work unless you're talking about very small updates. It's not a very good way of handling rotations. And so we're going to actually look at quaternions, which is an alternative way of representing rotations that actually allows us to do a very convenient operation called a slurp, or spherical linear interpolation. Okay, so there's our x and y, and you notice basically the only difference between the two is that we would consider the z-axis to be ignored, or the x-axis. Okay, and then we have what's called the general rotation matrix. And we should pay attention to this because this is going to come into play later when we talk about quaternions. But this is called the axis angle representation. And so if you had a vector representing the axis that you wanted to rotate around, then you could just say, okay, this is my axis that I'm rotating around, and then you can just spin it around that axis, which is very handy. And so if you wanted to, you could also just throw in, if you want to rotate around the x-axis, and you just put the vector 1, 0, 0, or if you want to rotate around the z-axis, 0, 0, 1, and this will reduce back to the matrices we just saw earlier. So this is a general purpose. You can put whatever angle you want in there, or a vector you want in there. You can get the x, y, and z. So if you're going to implement one rotation matrix inside a 3D program, it would definitely be this matrix, because you can get all the other ones from it. Okay, then this particular matrix, the ortho matrix, so this has to do with projection. So this is where we would like to go from 3D coordinates to 2D coordinates. So we can use a matrix that actually gets all that math ready for us. And so this one, we basically can take a look at Tx, just represents this fraction, right plus left over right minus left. Let's just think about what that means. Let's just say right was 1980 and left was 0, okay? We would see that Tx would just equal 1980 over 1980. So that one would normally just become -1. So we would like the, we just want to offset the x coordinates by -1. And then Ty is almost the same thing, right? 1080 plus 0 over 1080 minus 0. So that's just going to be -1 as well. And I got to move this around. TZ, this is different because we have this concept of far and near that has to do with what is your clipping plane. So how far are coordinates allowed to go and how close are coordinates allowed to go. And by applying this equation over here, this will just, if you notice, then we have a scaling matrix in the upper left-hand 3x3 matrix. So we can see, okay, divide 2 over, say, 1980 by -0. So we're basically scaling by the number of pixels on the screen and then multiplying by 2. And what's going to end up happening is then all our coordinates are going to go from -1 to +1 on the x-axis, -1 to +1 on the y-axis, and then z is just going to represent 0 through, or actually in this one, it's going to represent 1 to -1. We actually flip it around because we want negative z coordinates. So this matrix, you know, it looks a little weird, but if you just think about it in terms of pixels, then this is just our way of mapping the screen so that we could represent, you know, we could either represent exact pixels on the screen or we could represent like a mathematical, you know, if you're doing math and you wanted to say, I'm making a graph from -4 to +4 and from -4 to -2 to +2. So you can adjust it your ortho basis so that it works on your screen. Okay, so the opposite though, the perspective, we talked a little bit about this last time, is this is if you want to project to the screen. In other words, you want to have a pinhole camera and you have a certain aperture that you want to get. So maybe you're concerned with 90 degrees or 45 degrees or whatever you want to get. We're simulating a pinhole camera. And this one, you notice, looks a little bit different. The scaling matrix, we actually use the cotangent of the field of the vertical field of view. So we'd use, like, if it was 90-degree field of view from top to bottom, then our F would be the cotangent of 45 degrees. All right. And then we put our aspect ratio in there. Okay. And then we have our Z looks very different though than last time. Okay. We were just offsetting Z with ortho, but now with this Z, we're actually scaling it so that we can get values between 0 and 1. That's the whole purpose of this matrix here. And that's going to allow us to use the depth buffer where we can compare. If we're drawing a polygon at distance 5 or 0.5, that's closer than a polygon that's a distance of 0.7. So we can distinguish which polygon should be drawn over the other one. And by picking appropriate values, we talked about this last time, is you can affect how many bits of precision that you're actually able to use. And we'll show what that looks like when we talk about the depth buffer. Okay, and then we were talking about moving through space, all right? And so over here, you know, we might be in object space. That's where our coordinates are located in a model. So when you're in Blender or something, your coordinates are centered around its own like pivot, and that's how we save it. And then we have a world space where we can say, let's take a matrix to move it out into the world. So maybe the chairs are defined in relationship to a local origin, and then we can say, let's use a matrix to decide where we're going to put each chair in the room. And then we have view space. So this is where are we going to put the camera inside the room. And the view space is actually going to be the inverse of whatever its world space, the equivalent world space matrix would be for the camera. So that inverse comes really handy for view space. And then projection space is how are we going to show this on the screen. Okay, And we normally use a matrix for each of these. All right. Okay. And we were talking about the different axes inside the matrix. So I'm not going to go into that right now. That's transformation. Okay. But I wanted to talk about what happens after we get to the projection part. Okay. So we multiply the matrix, the projection matrix times the view matrix times the world matrix, and then we multiply the our local space coordinate, and now we're ready to project that coordinate into two-dimensional coordinates. So here's what happens. First we have, and this is goes along with what's called the fixed function pipeline. Anybody heard of the fixed function pipeline? No? Okay, anybody heard of the programmable pipeline? Okay, so in the 90s, you had a lot of specialized graphics hardware, I guess late 80s as well. You had specialized graphics hardware that would accelerate some of these, matrix routines and hardware, and it would just do it per vertex, okay? And so they basically standardize how this stuff works through the pipeline. Nowadays, it's all programmable, so we have to actually say, do these operations. But it used to be you could just say, here's what the world matrix is, here's what my projection matrix is, and you're good to go. So, we're going to look at that process, but it works the same with the programmable side for all intents and purposes. So we have the object coordinates, all right, and I just use a little t here to represent the transpose. And we want to go to I coordinates. So we use the model view matrix. So this is going to have the world matrix and our camera matrix put together. So another term for a camera is a view. So you'll sometimes just see like matrix camera or matrix view. It means the same thing. And so we basically apply our transformation here. We get I coordinates. And then we need to go from I coordinates to clip coordinates. So this is where we multiply our projection matrix. And at this step, we want to clip the coordinates. So anything that's like outside of the range of our view space, we can clip those. So if you can imagine a polygon, being drawn a little bit off screen, we don't want to draw the part that's not visible. So we clip that off. Okay. In the same way that you get a pair of scissors and trim, if you're trimming, maybe you're drawing a triangle on a piece of paper, but some of it's going over the edge. Clipping is just chopping that part off, so we can draw only what's on the screen. Okay, so after we've done this, we have clip coordinates, and now we want to do the perspective division. And we talked about the perspective division. Maybe it was week 1 we talked about it, or it could have been last week. No, I think it was week 1. And I said just divide by z. All right. However, you see over here that it's divide by w. All right, and we're like, okay, this is weird. But the reason we're doing this is because we're using homogeneous coordinates. And if we look at our matrix, let's just take a look at our projection matrix. If you look at the way this is going to behave, this last column is what's going to form our z coordinate. Okay, so if we look, 0 times x would be 0, 0 times y would be 0. This times our z coordinate is going to map it between 0 and 1. And then 0 times w is 0. So we basically are copying the z coordinate into the w coordinate. All right. So that's the purpose. This one doesn't do that. If you notice, we preserve the w coordinate on the ortho view. But on the perspective one, we are copying the z coordinate into w because we're going to do this perspective division. All right. So going back over here, so you see over here that we get to what's called device coordinates by dividing by w. So now x and y are divided by z, and our z coordinate is basically going to, we're going to remap that range for us. Okay, so now we have device coordinates, but device coordinates still needs to be mapped to the screen. So if we're doing perspective and we're doing a square frame buffer, then our coordinates are going from -1 to +1. So now we would need to scale that so that it fits inside our frame buffer. And so if you notice over here, we have two sets of coordinates. One's called the pixel center. So that's the, think origin on the screens, OX and OY. And the viewport width and height, PX and PY, okay? And you'll notice that the OX, we say that that's the same thing as X plus W over 2. So X is normally 0. And so W over 2 would be like, 1920 divided by 2 is at 960. And so, basically what we're doing is saying, okay, take the width over 2 and multiply that by our X, and then add the center of the screen. Okay, so we're basically going from coordinates that go from -1 to positive 1 to 0, 0, and then say 1920 by 1080. So this little equation over here will map that for us. And then this last one is going to map our Z coordinates so that they actually lie between 0 and 1. And then that's what we're going to use for the depth buffer algorithm. Okay, does anybody understand how projection works? We got this huge process, but it really, the underlying principle is that, one, we need to divide by Z, so we copy Z into W. And then two, we need to adjust the device coordinates so that it actually maps to pixels on the screen, okay? So we have device coordinates and we have pixel coordinates or window coordinates. Okay, I'm going to skip that. And we're going to talk a little bit about quaternions, and then I'm going to go into GLFW. Anybody have any questions so far on 3D math? Fun stuff, right? This is if you're doing like everything from scratch and just kind of like, not very many people write 3D engines from scratch anymore or software-based engines anymore, because you'd have to do all of this stuff. Okay, so quaternions are, they're very fascinating to me. They were invented by William Hamilton in 1843. And so rumor has it he was walking to a meeting, and as he was crossing this bridge, this formula came to him as he was thinking about this quaternion problem. This formula is I squared equals J squared equals K squared equals IJK equals -1. That's the rules for his mathematical system, all right? And so you could represent a 4 real numbers, A, B, C, and D, and I, J, and K, they represent axes like you would think, okay? So I would represent the x-axis, J represents the y-axis, and K represents the z-axis. They all represent that. And so although they are called quaternion units, and I already introduced you to these basis vectors, E1, E2, and E3, so that they would correspond to that. And it's the foundation of its own algebra, which you might see in what they call blackboard bold H. All right, so it looks like an H that's been double striped. And so let's see what we can do with them. Okay, so one, we have special rules. So if we were to have like I and I, it would equal -1. So if you studied complex numbers and they said, yeah, I squared equals -1, and you're like, okay, I'll go along with it. So we're going to kind of go along with that idea. But instead of having one complex plane, it's like we're having 3 of them. And on top of that, then we could say that, if we had I and J, then if we were to multiply I, J together, then we would get K. And if you think about it, the cross product is what makes that possible, because if you were to take the cross product of I and J, you should get the K vector out because it's perpendicular. All right. This is why it's important to understand why the cross product operator works the way it does. And that's the way it works in this algebra system as well. Now, if you flip it and you instead you had J times I, then you get -K, which if you're doing the cross product and you have A times B, the cross product of B times A is actually -A times B. So it points the opposite direction. So if you do the cross product in the wrong order, your vector points the other way. And it's a weird phenomenon that people have a hard time understanding. Like, how come these vectors act this way? But we talked about why that they don't act that way is because it's not really a vector, it's a bivector. So, and a bivector basically operates like on the other side of that mathematical issue there. Okay, so now we're interested in actually calculating the product of two of these quaternions. So what is, you know, A plus BI plus CJ plus DK? If we have that form, how do we multiply two of these quaternions together? And what does that do for us? So here's the worked out math, if you will. So I have these two vectors, and I use the exact same kind of math that we used for the geometric algebra. And when it's all said and done, actually I think it got clipped off the bottom here, but the idea here is that it combines some of the dot product and some of the cross product in there. So like you can kind of see those parts. Like for the real component, you see AW times BW minus AX BX minus AY BY minus AZ BZ. That's just the dot product of A and B, if you will. So let's take a look at this next one, where I kind of have a little summary for that. So here's some more operations you can do. So there's ways to kind of prove to make sure that the math works the way it's supposed to. And recall, we said this is like a brand new algebra system. This isn't just like what you learn in, you know, grades 1 through 5. This is like new stuff above that. And so what we might say that a quaternion can be broken into its scalar part and its vector part. So the scalar part would represent the A, and the vector part would be the B, C, and D. That's the vector part. So another way of writing a quaternion is just to say, well, it's the combination of the real part and the vector part. Okay, and remember we were talking about the angle axis matrix. You know, we give it an actual vector representing what it's rotating around, and this represents the same idea here. Although you might say, well, does R represent theta then? You know, and we're going to see that it doesn't 100% represent theta, but it's closely related to it. So if we wanted to add two quaternions together, we can just add the real parts and add the vector parts together. So that works the way we'd expect it to. If we were to multiply two quaternions together, then this is what it looks like, but this is what it means. So the real part is R1, R2, so the real part minus the dot product of V1, V2, which we saw that. And then the second part is we have R1, V2 plus, so we're scaling the vector part by the first quaternion, and we're scaling the first vector part by the second quaternion, and then we're adding the cross product to it. Okay, so you can see those ideas are all integrated into this. Okay, now there is this conjugate. We can calculate the conjugate, and we'll see what the conjugate's useful for. And basically it just means you take that vector and you just flip the vector around on this other side. So remember we said like A cross B is the same as minus B cross A. This is almost like saying, well, give me the other side of this quaternion, the side where the vector part points the opposite way. So, and just the way that matrix inversion works, or transposition works, where you have, say, Q1, Q2 conjugate, then you just flip the order around. So it's Q2 conjugate, Q1 conjugate. And the way that you would calculate the norm is you could take the square root of the Q times its conjugate, which if you look over here, this is like taking the length of the whole thing, A squared plus B squared plus C squared plus D squared. Okay. Are we all good so far? This is a bunch of strange math, I'm sure. This is not, we're not in Kansas anymore. Okay. So now if you wanted to compute the distance between two quaternions, then you can just subtract the two and then take the length, or take the norm. And then we have this idea of a unit quaternion. So just like we have a unit vector, this has the same property of you take a quaternion and you divide it by its norm, okay? So that it's unit length, all right? And then the reciprocal is, so this is like taking the inverse of a matrix, if you will. But the reciprocal then is the conjugate divided by the norm squared. Okay, so it's going to be interesting to see how these quaternions work, because it's representing matrix mathematics in a certain sense. All right, so here's what happens. If we wanted to, if we had an ordinary vector, px, py, and pz, and we wanted to rotate an angle theta around the axis represented by bc or d, but I'm going to call it ux, uy, and uz just so we have, so we understand what's going on here. Then the quaternion representation uses this Euler's equation, okay, which we can expand out. So this is the same thing as saying that sine theta over 2, and that's what the real component is, plus our axis vector times the cosine of theta over 2. So we are correct in saying that the quaternion represents this rotation. That real part represents the rotation around an axis. And so if we then wanted to rotate p, which is just some regular vector, then we could say that the new vector equals q times p times the inverse of q. And if we do this, then we can calculate, we can rotate p using this quaternion. But if you notice, I guess with this multiplication here is it's not quite as, there's a way to kind of make it get easier. What happens normally at this point is we just turn the quaternion into a rotation matrix. And if you notice this matrix over here, that it has a very similar form to the one that we just saw for the angle axis formula. And the reason why is because it all comes from the same place. So there's a guy, Rodriguez, it's called Rodriguez formula, and that's where this matrix comes from. So it's just kind of, you know, in the early 19th century, you have all these people working on these problems here. So they're basically done with gravity, and now they're kind of thinking bigger problems, okay? And all this work is going to be influential for like the 20th century when we start talking about relativity and all sorts of other mathematical concepts that we think about for later. Okay, so now we know how to rotate vectors with quaternions. This is how you might recover the original information. So if you want to find out what the original axis of rotation is, then you could just divide, you just take the vector component of q and divide it by that length. So this looks just like a normalization for a vector. And then theta, we can say that that's the same thing as 2 times a tangent 2 of the vector component. So we want to find the length of the vector component, and qr, the real component, okay? So that's what gets us our, and the reason why we're multiplying by 2 is because sine theta over 2, all right? Okay, so this is how you take a quaternion and basically turn it back into 3D information that we might find useful. So here's where they become really popular. So in 1985, people are trying to, Ken Shoemake was working on how do you rotate objects along a path. So you want to represent an object moving along some kind of spline inside of a scene. So if you're imagining a roller coaster might need to move along a spline, you want to animate that. So the problem that we come across, like, let me just back up here. How do you take a matrix like this and interpolate from one matrix to another? Like, can you just do that? Can you just blend 2 matrices together? What do you think? Or is your little red alarm bell going off? No, that doesn't sound like something you should be able to do. And you would be correct. You don't just take 2 matrices and just blend them mathematically together, okay? But you can do that with quaternions. And so I'm going to open up this page here real quick so we can see the original paper from 1985. He worked for the Singer Company, Link Flight Simulation Division. Is that the same company that makes Singer sewing machines? That's kind of funny. So he describes this thing called spherical linear interpolation. And the idea here is that, and I'll show you this equation here. I'm just trying to find a graphic that illustrates what what they're trying to do. Here we go. So basically what we want to do is we'd like to rotate, or we'd like to animate something along a path. But we can't just do it with a matrix. You can't just blend the matrices together. So what you can do, though, is you can blend the quaternions together. And the way that you do that is, we'd like to use a value between 0 and 1. So I just copied these formulas out from the paper. And the spherical linear interpolation then is just, we can just take the angle, so sine of 1 minus u theta over sine theta times q1, and you can see this is just blending the two angles together. And so if you had two quaternions, let's just say one was pointing up here and another was pointing over here, instead of getting that gimbal lock that you'd get by interpolating the x, y, z axis of the Euler equations, you get a smooth line going from one quaternion to the other. And that is the killer application for quaternions in computer graphics, which is why you see them in like Unity as like, they do quaternions, because it makes the animation part easy to kind of handle as far as the math goes. Okay, so you can't just blend the matrices together, but you can blend the quaternions together and get a smooth animation result from it. All right. Okay, so, but one thing we didn't answer for this is how can we use these slurp with splines? And that's because we haven't talked about splines yet. So I would encourage you, take a look at the Shoemake paper. It's very good. It's one of those foundational computer graphics papers, and just kind of get an idea of, okay, this is how they would do animation. But as we go later in the course, we'll take a look at how splines are evaluated mathematically. We'll take a look at Bezier curves in particular, and kind of see how you might use these to kind of smoothly animate a camera or any kind of object inside of a 3D scene. Okay, and there's a picture of splines. So this is what you can do with splines. And this is nice, because if you had a quaternion here and a quaternion here and a quaternion here, a quaternion here, then you can smoothly make some kind of animation that follows that path and looks natural. Okay, any questions on quaternions? We're going to look at, I'm trying to build some examples, some 3D examples, so we can play with them. Okay, so we're just not there yet, but I'm trying to work on some like 3D demos of quaternions in action. So that's one of my personal goals, is to animate a camera along a quaternion spline path. Yes? From their position. Sure, you could do that. Sometimes you can just represent that with a. That would be a good way to smoothly move the camera to another position and make sure that the rotation doesn't take some crazy path to get there, like you would. And we'll see when I get this demo ready. We'll be able to see the difference between using Euler angles to represent a rotation and using the quaternion. And it'll be very obvious why the quaternion is like, yeah, you wouldn't even bother with the Euler angles. You can use the Euler angles if you're trying to make small adjustments to a position, and that'll actually let you fly an object through a scene. But it's not any good for doing smooth animation, because you can get that gimbal lock problem. All right. Okay, so last thing I wanted to do was go to Visual Studio, and I wanted to just show, well, actually I have another slideshow presentation here. So I'm going to call OpenGL tutorial. We're going to start this today, but then we'll finish it on Wednesday. Okay, so we can actually see it happening in action. So in order to use GLFW, you typically need to use a few extra libraries. So the libraries installed on everybody's system is OpenGL and the OpenGL utility library, or GLUE. So GL and GLUE. You normally don't have to do anything to get those. You do have to do something to get GLFW and GLEW. GLEW is an extension library, so if you want to use all the fancy features of OpenGL, you have to use the extension library because it actually goes out and finds out where all of those functions are located so you can actually call them. Otherwise, you're stuck using what we call classic OpenGL, which is fine for some very basic applications, but you won't be able to do anything that you're thinking of doing without it. And then you have GLFW, which is a framework library for actually making programs that use OpenGL. So I'm going to talk about a very simple kind of program, the kind of program that you might want to like set it up so you can just say, here, put this as my title, and let's set this as the resolution. And then we can initialize the program, and then we go into a main loop that just repeats until we quit. And the setup is just, I have a program called GLFW template that I'm working on that make it very easy to just start up doing this kind of programming. So I'm working on this right now. But, you know, you just set some basic things like what should the resolution be? What should the window title be? And when we call the init function, then the first thing we need to do is initialize the library. So if it doesn't initialize, then something's probably very wrong with your configuration of your system. And it'll just say, okay, nope, we're not initializing anything. Let's get out of here. However, if that does succeed, then we can go ahead and create a window. And so over here, we can pass the width of the screen, the height of the screen, the window title, and we don't need to set anything for monitor share. So we set null for those. That would be something for something more advanced, probably if you had multiple monitors and you're trying to make sure it goes to one monitor over the other, or whether you need to share the context. Okay, and the context basically is the object controlling OpenGL. You might need to share the information with another library like OpenCL, which is for computing. And after we do that, then we need to make that context current. In other words, that window that was created, say, put an OpenGL context on this window. And if you remember last week, I was talking, or it could have been the first week, we were talking about graphical user interfaces. Typically, if you're using Direct3D or OpenGL, it takes control over the entire window. So you can't just say, let's put a GUI widget on top of it. This doesn't exist. Because what happens is that the graphics card is reserving a memory buffer for rendering right into that memory buffer. And then we display that whole memory buffer straight to the monitor, as opposed to letting the operating system control it. Now, if you're using WebGL in your web browser, what's happening underneath is you have the web browser is actually layering everything on top of each other. So when you render a WebGL buffer, it actually is then going to overlay other components on top of it. So if you want to do easy GUIs and reach a lot of people, then WebGL is a great way to go because you can just put controls right over it, and it is pretty straightforward. And all the skills then you learn are directly applicable to just about anything else you do with web development. So that is an option. And I've taken a look at that option with I have a WebGL library that I'm working on that kind of makes it easy to do that kind of stuff. We could probably take a look at that a little bit later, though, maybe next week. Okay, so after we make the context current, then we need to set some callbacks. So we need to have some way of intercepting things like, was a button on the keyboard pressed, or did the mouse move? Did somebody press a button while it was over the window? And what happens if the window gets resized? All right, those are things we need to pay attention to. So for the first one, the key callback, we have this particular form. So we pass the window, the keys, scan codes, whether shift key or anything was pressed. And in this very simple case, I just checked to see if the escape key is pressed. So 27 is the ASCII code for escape. And so you can just check for 27, and you hit 27, and we can just say, we're out of here. Okay, so we just set a flag that we should exit the main loop. The mouse button, this is something if we wanted to handle, like dragging or something, we'd have to do some more logic for handling those. If you notice, so I have to do something here, right? But that just goes to show you that how much you have to recreate from scratch if you're writing graphics applications, you know, you don't just get a double click out of it. You have to check the time that it clicked and then see if you got another click within an extra time. And so this is why I encourage you, do something simple at first, you know, capture up, down, left, right, you know, use the keyboard, or, you know, make a simple control scheme for your games so that you can handle, you don't have to handle a complicated input system. Okay, then we have the window size callback. So this is important because we would need to call the GL viewport function to say, here's where we should be drawing in the viewport. So if we resize the screen 33% larger, if we hadn't called GL viewport, we'd still be looking at the same size screen in the window and have a black border around the rest of it. So we need to tell OpenGL that we resize the window. Okay, so now in this is what would be the start function, but the main loop. And what we would want to do here is, first of all, I think it's important to be able to time certain parts of your application. If you don't time your application, then if you're on a faster computer or a slower computer, it's going to run faster or slower, which is not desirable. You often want things to run at a fixed speed. Okay, and so the two things that we're looking at in this loop here is whether the user clicked like the X button in the corner, so that would be something that JLFW will record for us and tell us about, or maybe we have an internal flag, like in the keyboard function we said, if we press the escape key, then go ahead and exit the loop. Okay, so as far as the timer goes, all we do is we're just measuring the elapsed time between frames. So we measure T0 and then we measure T1. And then we take the difference and then we just copy the T1 back into T0. That way next time we're constantly measuring how much time happened during each frame. And so this is a good time to then update our scene. So maybe we're doing some rotations or something and then rendering the scene. And then we can swap buffers. So a lot of times we render into one buffer and then as a whole we move it and make that the main screen. And what this will help us avoid is tearing artifacts. We allow basically the graphics hardware to smoothly go from frame to frame. Sometimes we'll do triple buffering where we're rendering several frames in order and allowing the system to kind of go along with that. Now, if you're rendering like 60 frames a second, you're talking about 17 milliseconds. So you do have to think about lag in terms of if you're doing double buffering, technically there is a 17 millisecond lag between the time you are processing the input and the time you could be displaying the image. But typically, either you'll just be filtering through user input faster than that, or the person doesn't notice the difference unless they're an expert. Okay, and then we poll for new events. That way we can process the, if the window is supposed to be closed and so on. And lastly, we call GLFW terminate to finish the program. Okay, so I have an example program here. I'll just go ahead and run this. And this is a little bit more complicated because it's doing a few more things. But inside the main loop here, I'm taking the time and I'm just doing a simple little function on the red value. So I'm calling OpenGL and I'm saying, let's set the clear color. So instead of having a black screen, I decided let's have something a little bit more so we know something is happening. So I do a little cosine function on the time. That way we can kind of see it cycling through the red going up and down in value. Otherwise, I said green to 0, blue to 0, and the alpha value to 1 so that we actually see what's being drawn. And then I clear the screen, and this will set the whole screen to that color. Okay, so if I run this program, then your screen is going to look like it's not smoothly going up and down because of the lag on the video, but this basically is like the video we watched at the beginning, our black screen, not a blank screen, a black screen. Okay. And, then we can kind of build up from here and see how graphics applications are kind of built. So we're kind of working. And then if I hit the escape key, then the program just quits. And I'm just looking for key number 27. Okay. So just to wrap up for today, we kind of tied it back into how hard it is just to get a black screen. But we also reviewed some of the math we talked about from last week, covered what our homework 2 is going to look like. So as soon as I figure out what that last additional requirement is going to be, then I'll post it up on Blackboard, so you can go ahead and start working. I would encourage you, if you don't have a working program from this last weekend, please try to get that finished and send it to me so that this weekend, when you work on your game, we can kind of actually get a finished game going this time around. And then use that helpful diagram to kind of help you plan what you need to figure out, whether you're using Unreal or Unity or Panda or whatever the case is. So, all right, are there any questions? All right, so I'm going to go ahead and end the meeting here.